Alright, we should be going live. Okay, so today's stream will start from basically the recap of what was before, and then we'll go straight towards like the next parts of the presentation, which was about solving combinatorial optimization problems in practice, various algorithms, and etc. Okay. So we had basically a recap, the most important things, the difference between decision problems and optimization problems. So they are they are interconnected with each other. They share many similarities, but the most important thing to grasp about them is that decision problems are a special case of, or maybe a modification of optimization problems, because decision problems ponder about the existence of something, that is, whether, for example, a path of length x or less exists from point A to B, and the answer to the decision problem is always a yes or a no. Optimization problem would ask about something: what is the shortest path length between A and B. Here we don't have a threshold with the optimization problem. Decision problem does have a threshold, and whether this condition is satisfied determines the answer being a yes or a no. Now, so that's basically the difference between them. So the search problem, basically finding something, there's a problem pi, a set of finite instances of this problem. For each instance there is also a set of finite set of solutions. Algorithm A solves the search problem pi if for each instance I returns answer no, blah blah blah. Otherwise A provides some solution little z that belongs to the set of solutions. So basically, if a solution to a particular instance does not exist, it returns an empty set. Otherwise it returns some solution z. Like so the empty set is the special case when the set of solutions for the particular instance is empty. So solutions for a particular instance do not exist. Like there are none. No algorithm will possibly return it. and if this set is not empty, so if there is at least one solution, it will return some solution little z from this set of solutions on that instance. Any decision problem pi can be rendered as a search problem by defining this set of solutions as yes if the instance belongs to, like, whatever this is. I mean, essentially it's in plain English it means something like among the lines, if we set a threshold on an optimization problem, then we can convert these answers to be yes or no, depending on whether they cross the threshold. In search problems, different objects yes and no answers return as solutions, blah blah blah. Hence, we cannot use polynomial transformation to show equivalence of search problems, because polynomial transformation preserves polynomial time yes-no answerability. Yeah, but yeah, welcome. Yeah, currently doing a recap, basically what we did in the previous stream, but just shortly before we catch up to the 80-something page and we just continue onwards. So polynomial Turing reduction, I said in the previous stream that it is a way to accelerate the algorithm. It is not. It's just a way of representing the algorithm. No, it's representing a problem in another problem. So if it's possible, this is important when we are working with NP classes. So NP easy problem can be represented in some NP hard, an NP problem. NP can be represented in some NP complete problem, and NP complete problem can be represented as some NP hard problem, and so on. So that's that. So decision problem pi1 is NP complete, and can the optimization version be easy? Polynomial answer is no. Optimization version is usually as hard as the decision problem, if not harder, because decision problem can terminate faster than the optimization one on a usual basis. NP hard problem, yeah, if there's a problem pi prime in NP complete such that this problem can be Turing reduced, like T reduced to pi. Basically NP hard problems is a much larger set of different problems. That not all NP hard problems are in NP, but the problems that are NP hard and are in NP are NP complete. Yeah. Basically, this is a proof that sometimes we can actually prove that the decision, like optimization knapsack problem, has the same, or it can be reduced to a decision knapsack problem. It's not always the case though. So here this proof used a lemma with an intermediate like extension of the problem, and by chain reduction it's proven that like this can be proven to this can be reduced to that. Yeah, NP easy. So these problems can be just reduced to other NP problems, like some NP, like to some NP problems at least. Strong NP hardness. Yeah, this thing. This was mentioned only a few times, but this means something like strong NP hardness when the the input is not bounded by a polynomial. So Am I right? The hypothetical procedure P must preserve the constraints of the pseudo-polynomial transformation. Reduction in pseudo-polynomial time instance size is not exponentially reduced. Biggest numerical value is not exponentially increased. I'll just ask real quick, chat, about this. I mean, we are just about to catch up. I think we won't spend more than 30 minutes on this. Some additional information. Never mind, I'll check this out later. Yeah, summary definition of NP-complete, NP and NP-hard problems. No, NP-easy, NP-hard, NP-equivalent. So NP-complete can be reduced to an NP-hard problem. NP-easy problems can be reduced to NP problems, and NP-hard problems can be reduced to NP-hard problems that are NP-hard and simultaneously NP-easy are NP-equivalent. Yeah, relaxation, which basically allows us to find specific variants of the problems that we are able to solve much easier. Because of with exploiting some properties of these problems or something like that, it helps to, as the paper says, to delineate the border between easy and hard versions of some problems. Why relaxing? Again, deterministic scheduling. This is basically this Mach-Newton's algorithm. So, optimum schedule length, which is basically the maximum among. So this is bounded by either the average of the average of the sum of the jobs. So it is, if we have m processors and we just summate all the time for all the jobs, Then the most like optimal packaging of this workload would be to distribute the workload evenly between the processors, and so this is why this 1/m comes from. But this is also bounded by the time of the longest job, so whichever is greater will take this will take the value, or rather this will assume the value of the bigger one, and this like the ratio you can get won't become any better than this Cmax star. Start constructing schedule on processor I at the time 0. While there are unscheduled tasks to do, choose an arbitrary unscheduled task Tj. For example, with processing Pj. Append Tj on the current processor at the current time. Here. So if the current time plus Pj is less than this Cmax star, so whether when this is less than the optimum schedule length, T becomes T plus Pj. In other words, Tj is scheduled. Or else this task would have to finish after Cmax star on the current processor. So we are basically trying to distribute the workload as evenly as possible, not to cross this optimum schedule length. We just move to the next processor if the current QU for the current processor would become too long to accommodate this new task. And schedule piece of task Tj on length Cmax star minus T on processor I. So essentially we are just scheduling the rest of this task, like just to pack as much time here, not to cross this optimum on processor I. So this is the remainder, and we will move this remaining part of the task to the next processor. Yeah, put on the new current processor the remaining piece, and undo. Yeah, so yeah, adjustment to a preemptive schedule. So the non-preemptive case would be a bit challenging, because here the algorithm just here it simply frees the resources. So no, it doesn't freeze the resources, it moves the remaining part. It wouldn't be able to do that on the non-preemptive case. Yeah, basically the hierarchy of the complexity with different parameters. So we either change the type of machines, like constraints, blah blah blah. all that flow will be at least as difficult as the one before. So yeah, if a problem is represented by some boxes NP hard, then all its successors are also NP hard because they are more general cases. Yep. Definition of the knapsack problem is convoluted notation, but it essentially means that this is the maximum value among the elements that fit this constraint. Yeah, finite solutions, finite instances, and the set of the value of a solution, which can be measured. Pardon me. Okay. Okay. Here we are again. So this is a performance ratio about the optimum value for a given instance and the one achievable by the algorithm. So the bigger this ratio is, the worse the algorithm performs. Ideally it would be just 1. Absolute worst case scenario is just the worst performance ratio among all instances bounded by this R. Asymptotic worst case performance scenario is basically exactly the same, but it introduces some threshold Z that basically is concerned about only the large instances. It ignores the small instances where the algorithm may perform differently. Parallel identical processors, set of n non-preemptible tasks with standard features, processing times pj ready to be executed at time 0, no deadlines, blah blah blah. Let me just fire one thing real quick. Okay. Let me test something. Okay. Let me test something. Okay. Okay, and back. Here we are back. So, respective fields in notation P double pipe C max mean P is just parallel in identical processors, so each are equal, they have equal processing times. Pipe is basically the set of non-preemptible tasks with standard features. Processing times PJ ready to be executed at time 0, no deadlines, no special resources needed, no precedence constraints, etc. Cmax is the schedule length. Cmax schedule length is the optimality criteria. List algorithm for P double pipe Cmax put tasks on a list according to some order. Assign tasks from the list sequentially to free the processors. Yeah, performance ratio. This is the proof that this performance ratio of this algorithm is 2 minus 1 over m. So it will find at worst, asymptotically it will find the solution that is twice as bad as the optimal one. So essentially x is bounded by this, so it will be always less than or equal to this ratio minus y, maximum length of schedule with in which all processors work. Yeah, so it will be it will never be better than this. This is always less than or equal to the optimal, because I mean this is the perfect world, and again y will not be greater than the length of any task, any single task, because for example if we had as I said on the previous stream, if we had let's say 4 processors, 1 working and 3 idling from the start, then y would be equal to the length of this single task. Yeah, so I just don't know where this comes from. I think it's okay. So this is the maximum among the instances of the pi. So this is the maximum ratio x plus y over optimal. This is always less than on basically this because of this is always less than or equal to this. We just pull here y from this fraction, and then again based on this assumption we just change this, so this is always less than or equal to opt in both cases, because this ratio is always less than or equal to the optimum schedule. And this, just dividing by opt, is equal to 2 minus 1 over m. Here's the proof for that. Longest processing time. order the tasks according to the non-increasing order of processing times pj. Assign tasks from this list sequentially to 3 processors. So asymptotically it's just 4/3, which is not bad. So each task is basically assigned to each processor, so first processor gets this, so yeah, they are basically going one by one until the end. And here we have this this gap, the idling time. Performance ratio for vertex cover. Need to verify it again. This ratio is supposedly less than or equal to 2. No, this particular algorithm. I don't get this since no pair of edges in X is incident. Optimum cover requires at least as many vertices as the number of edges in X. No, at least as many vertices as the number of edges in X. Okay. Never mind. I guess that works. I'll come back to it later, but generally these were the proofs that about these ratios. I'm not here discovering or reading these proofs, but I know they are there and I know their origin. Now this approximation schemes. For optimization problem pi is an algorithm A epsilon that for a given instance I and accuracy with epsilon greater than 0 outputs a solution small z that belongs to this set of solutions such that performance ratio will be less than or equal to L plus epsilon. This does not say anything about the time required to reach such a solution. And polynomial time approximation scheme, PTAS, is an approximation scheme, and for each fixed epsilon greater than 0, A epsilon is a polynomial time algorithm. So this basically approximation scheme with this one thing that A has to be this polynomial time algorithm. FPTAS. A epsilon runs in time bounded by a polynomial function of instance size n of I and 1 over epsilon. So yeah, we have also the constraint on the size of input and the epsilon. This ratio 1 over epsilon. Yeah, works for me. Sorry. Yeah, so here it talks about that some problems can be solved with these polynomial time approximation schemes. No, they admit these schemes. Some algorithms even have constant performance ratio, but some do not have it at all, and these are bad. So algorithm does not exist that has this ratio less than infinity. Best achievable asymptotic performance ratio. Infimum amongst the instances. Infimum amongst the some set of algorithms. Oh, and these are these postulates. So for the case of as best achievable performance ratio equal to 1, the following special case can be distinguished from worst to the best. PTS exists for pi, FPTS exists for pi, algorithm A with performance ratio of assembly performance ratio to 1 equals 1 exists for pi. Problem pi can be solved by a polynomial algorithm with guarantees that this like the solution yielded by this algorithm minus the difference between this it and optimal solution will be less than k, where k is some constant. It can be shown that for some problems certain types of approximation algorithms cannot exist unless p equals to np. Examples follow. If p does not equal np, then no polynomial algorithm A for knapsack can guarantee that this time achievable by this algorithm minus the optimal solution is less than or equal to k, where k is some constant. By scaling or rescaling k plus 1 times values wi. This is, I think, concept of dynamic programming. Okay, so asymptotic ratio is always less than or equal to the absolute ratio because of these anomalies, pesky anomalies. Yeah, decision framework, blah blah blah. It's not that bad. Now that I look at it, it was really tough yesterday. But now I basically this recap took, I think, I mean not half an hour, but something about an hour, and yeah, it's already pretty good. This last slide.
Kobieta.
Mężczyzna. Chłopiec.
Dziewczynka.
You had to join, I think, at least or at most a few minutes ago. I had to deal with one technicality as a side gig, so that's why I've been silent for the past minutes or so. In terms of recap, I would say it's going much better than I anticipated. Right, so the recap is done. Set dpi of pi instances called problem space, set A of algorithms for pi called algorithm space, performance measure P, which is basically a combination of these instances and the algorithms that gives some results. A mapping it's a function S from this set of instances to a set of algorithms. Okay, so this concerns basically the selection of an algorithm, my best algorithm for a particular problem. In the alternative formulation given is additionally for the set of instance characteristics fi called feature space f, then mapping S from F to A, which maximizes the performance. The performance measure based on these features. Runtime and solution quality are typical performance measures in combinatorial optimization, yet they are mutually interrelated, hence ASP is a multi-criteria problem. Example features in feature space F for graph problems, number of nodes, edges, graph density in vertex space. Okay. For the above formalization of ASP, choosing the algorithm is instance classification problem. I don't know whether this is implies how to read this. Okay, wait, how to read this again? Formalizing the algorithm selection problem involves choosing the algorithm instance classification in machine learning. Okay, that is if algorithms A belonging to algorithm space have classes dpa that are the subset of dp of instances. So this dp is the set of instances pi, not p, the pi problem space, which are solved best by this algorithm A, then assign class dpi a to each instance I belonging to dpi. Yeah, so basically we are selecting best instances that this algorithm can solve. Machine learning SVM recommendations about which algorithm to use in each region. We can clearly see that some algorithms excel much better than the others. Ant colony is here. Hill-Climb algorithm is here. I don't know if it is partial colony, taboo colony, something like that. Hill-Climb. None is here for some reason. I don't know what it does mean. Greedy algorithms and matroids. Matroids. Let's reiterate. Greedy algorithms have the following features. A solution is constructed by adding elements one by one. The added element respects the constraints of the solution and minimizes, respectively maximizes some objective function. Greedy algorithms are single pass. An element added to the solution is never removed. After constructing the solution, greedy stops. Only one solution is built. They are fast, in other words have low order polynomial time complexity. Yeah, we dealt with these greedy algorithms a lot. It appears that greedy algorithms can construct optimum solutions for some problems. How come? How can they manage if so many combinatorial optimization problems are hard? What features such problems must have to be solved to optimality by a greedy algorithm? I guess sufficiently simple. Minimum spanning tree. Given graph with G with vertex with number of vertices V and edges E with weights W, I, J on edges, find a spanning tree. Again, spanning tree connects all vertices of G of minimum sum of weights of chosen edges. Prim's algorithm. The idea is to add the MST to the MST the closest vertex. Weights W, I, J are interpreted as distances. Okay. Data structures. C with index I is a vertex already in MST. Closest to vertex I. Set of vertices not yet in the MST, which is V. Edge weights matrix. Ni is the neighbors of vertex I. tree is an empty, say, so double curly brackets signify an empty set. So the variable v is assigned the value of v minus 1 for some reason. For I going to v, I need a breakdown of this. Yeah. Remove an arbitrary starting vertex from the set of all vertices V. Start with an empty tree. This will eventually hold the edges of the MST. Okay. For every vertex I in V, initialize its cost Ci to infinity. Are you sure this is just one? This keeps track of the minimum edge weight that connects I to the MSC. No, I don't think so. I'll ask the universal primer. It's better at breaking down such concepts. Okay, so Primer says that this is assigned to 1, but in some implementations is infinite because you haven't processed any nodes. Okay, so until this set is not empty, while the set is not empty, we iterative building of the tree lines 3 to 8. Selecting the next edge, line 4. Here we pick the edge with the smallest weight that connects a node in the tree to a node outside the tree. Choose an argument with the I such that the value in any vertex P in V such that the weight of edge from P to so the closest vertex let's just stick to what Primer said. Here we pick the edge with the smallest weight that connects a node in the tree to a node outside the tree. Let's just stick with that definition. Argument finds the node P in V for which the edge weight WP to C of P is the smallest. Think of this as choosing the next town node to connect to an existing set of connected towns. The shortest road. It's some sort of analogy, I guess. Adding the edge. So the tree becomes itself with the added edge from P to the P to the closest edge, the closest node to P that is already in the MST. And this adds an edge. And V, that we remove P from V. For all J in neighborhood of P, if so if the edge between J and P, the weight of this edge is less than the weight of the edge from J to the closest node to J, the closest node to J becomes P. Improve CJ by choosing between old CJ and P, and we return the tree. Okay, so Prim's algorithm is, so the complexity is m plus m log n, because we have to use for example the priority queue to find vertex P in line 4, and in line 8 all edges are enumerated. So by clever arrangement of this algorithm we are able to accelerate it. So I think this is the best complexity. Kruskal's algorithm. Now this thing is on the list, so we need to study it carefully. This is one of the required algorithms, and one of the bullet points provided by as well as Prim. So Prim and Kruskal are both we need to study. Okay. Idea: add to the MST the lightest edge such that no cycle is created. What was the idea of Prim again? Add to the MST the closest vertex. Okay. Makes sense. Lightest such that no cycle is created. Problem: how to recognize effectively that a cycle can be made? In other words, how to recognize disconnected subtrees which can be connected such that no cycle is made. For this purpose, union find functions can be used. Union xy unites two sets, here two subtrees comprising elements x and y. So it's basically contains both without like if there's an overlap, it does not add them both twice. That's just that. Find x. Finds an element representing set, here a subtree comprising element x. Comprising. So I think, is that a neighbor of x? Set that contains x, in other words, find x operation determines which group or subset the element x currently belongs to. So yeah, find x just returns some element from the set that x belongs to. Very well. Okay, so union would just take as arguments two elements, x and y, and it would unite sets that these two are contained within amortized constant time, precisely in time O of alpha n, where alpha is an inverse function of Ackermann function, which values grow to the exponential. What? named after Wilhelm Ackermann, is one of the simplest and earliest discovered examples of a total computable function that is not primitive recursive. All primitive recursive functions are total and computable, but the Ackermann function says that not all total computable functions are primitive recursive. And computably speaking, primitive recursive function is roughly speaking a function that can be computed by a computer program whose loops are all for loops, that is, an upper bound of the limit of iterations of every loop is fixed before entering the loop. Okay. Inverse. Since the function f of n is equal to a of nn, considered above, grows very rapidly, its inverse function grows very slowly. This inverse Ackermann function f to the f minus 1 is usually denoted by alpha. So as said here, alpha n is less than 5 for any practical input size n, since Ackermann of 4 is on the order of 2 to the power 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 of 16. Holy moly. This inverse appears in the time complexity of some algorithms, such as disjoint set data structure. Okay, so this can be executed in a very, very small time. Wow. Wow. Okay. So here we have union, find parameter implementation by blah blah blah. This is the table called parents with that's of size n. Function find that takes an argument, integer argument u, which returns if u is equal to the parent of the u, then it returns u, or else it assigns parent of u to the what represents. Okay, so find is a function that. Oh, it's a recursive function. Wait a minute. Element representing set. Parent array. This array represents the parent of each element in the forest of trees. Each tree represents a set. Initially, each element is its own parent, meaning every element starts as a separate set. Okay, the find function. Purpose: to find the root or representative of the set that contains u. Base case: if u is equal to the parent of u, then u is its own root and we return it. Or recursive case, otherwise we recursively call it itself until we reach the root. Path compression. The line parent u is equal to the find parent u updates u's parent to the root of its set, flattening the tree. Union function to purpose to merge the sets containing U and V. Find the roots of U and V using find, then we update the root of U's to the point of the root of V's set. This effectively merges the two sets. I want to clarify. So this every element represents a vertex or node in the graph. So it would basically, the root of this tree is equal to the root of this tree. Okay, very well. You say that it's pointless to actually think about how this works? I mean, how would I emulate this or simulate this if I don't know how this works? Like, my point here is to understand how this works in principle. Because, I mean, if you don't, I mean, from my point of view, if you don't understand what you're looking at, it's useless. It's just basically tanking knowledge. Like, I needed to actually know that these represent the vertex and these structures actually represent trees. Okay, make set union link find set, and suddenly we are back to pseudocode for whatever reason. Code symbol represents the union find or disjoint set union data structure with optimizations, path compression and union by rank. Let me break down each function and explain its purpose in simple terms. Make set initializes a new set containing just the element x. Find set finds the representative of root of the set containing x with path compression to make future queries faster. Union xy measures the set containing x and y. Link, helper function for union, which actually merges two sets based on their ranks to keep the tree balanced. So if rank x is greater than rank y and the parent of y is x, tree rank, I think this refers to tree height, but I need to remember. rank in graph theory. The rank of an undirected graph has two unrelated definitions. In matroid theory, so what we are concerned with, of graphs, the rank of an undirected graph is defined as the number n minus c, where c is the number of connected components of I'll ask the chat directly. Rank? What is rank? Is rank? Value associated with each element or node that represents an approximation of the depth of the tree rooted at that node. It is used to decide which tree to attach to another node using link operation. The goal is of using rank is to keep the trees as shallow as possible, because shallow trees make the find set operations faster. Now shallow trees. What are shallow trees? Shallow tree is the represent sets. Each tree is a group of connected elements nodes where the root node of the tree is the representative of the set. Every node in the set points directly or indirectly to the root. A shallow tree is a tree where the tree height is small, ideally as close to flat as possible. For example, 1, 2, 3, 2, 4, 5. This tree has a height 4 levels of nodes. 1, 2, 3. This tree has height 2. Okay. So basically, it's the traversal time is shorter for those shallow trees. Okay. If rank x is equal to rank y is equal to rank y plus 1. Breakdown. By always attaching the smaller tree under the larger tree, the resulting tree remains balanced, minimizing its height. This reduces the time complexity of find set. Initialization. Okay, I think I got this, but I will come back to it later. Data structures. So Crosscall, again, you are adding the smallest edge that does not create a cycle to the MST. Okay, and for that we add the closest edge that is not in the MST. Yeah, fair enough. I mean, yeah, emulating this on paper. I mean, yeah, you have a point in that if he asks about this, just to implement or rather just emulate this algorithm, it's pretty easy. Like if we would like supposedly we had like a graph that has some end nodes, a small graph, it's unlikely that he'll like yield something difficult on the exam. Then we should be able to emulate this without this overhead. This is just these are technicalities if we wanted to implement this in computer, but or like a computer program, but to do a quick simple like simulation of this algorithm on paper, it would be easy because you just need an intuition, and for both of these algorithms, that is for the prims and the crosscalls, this intuition is fairly easy. And now the third bullet point, the Huffman coding, that was also mentioned by the professor. It's professor himself. Huffman coding. This is coding. We had this on information theory, but yeah, let's say the quality of my assignment was questionable at best. Huffman coding algorithm is used in lossless compression. Yeah, because it just uses as no information is lost anywhere. We just pack the information in a more clever manner. It's used in lossless compression by assigning variable length binary codes to the input symbols. Yeah, so it's based on the frequency of how often particular symbols appear, and we just the shorter, like the more frequent the symbol is, the shorter the sequence it gets, so that it uses the least amount of information when it's used most of the time. And it just increases in frequency. It increases in length, like the rarer it is. So symbols that are very rare will get expensive sequences, but because they are rare, they won't add much to the cost of the message. Notations. SI is the symbol I. PI is probability frequency weight of the symbol I. BI, number of bits encoding this symbol, and N is the number of total number of symbols. Huffman algorithm minimizes weighted length L of symbols string defined as. So this is the number of bits and probability. So it sums this sum like of the number of symbols and the probability. It weighted length L of symbol string. Okay, I think I got this. Yeah, basically, so this L function is minimized by this algorithm, where we take the probability, so frequency of the symbol, and the cost of the symbol. So symbols with high probability should have low cost, and we can afford for rare symbols to give them longer sequences because they just appear not so often, so they won't be contributing to the total cost as much. Huffman algorithm operation can be interpreted as a construction of a binary tree bottom up. Function Huffman: create n binary trees with nodes SIPI. So we have a binary tree for each symbol, and it contains 2 nodes. Wait, 2 nodes? Well, the number of binary trees is greater than 1. Join 2 trees of ij with minimum pi plus pj into a new tree t with Jesus. I'll ask chat to digest it for me. Though it's going pretty smoothly. We have still 60 something pages to go. But as I look at it, we are ending it somewhere here on the Dinic algorithm, I think. Dinitz. On the 164th page, so exactly here. Okay, we can then continue on our journey. It's not that bad, honestly. I thought that it would come up with greater resistance, but maybe I still don't know about what awaits us here. Maybe tougher than what's this. I mean, so far it's not that difficult. With this digest from ChatGPT, it's actually pretty good, pretty darn good. Create n binary trees for each symbol. Each symbol SI in your data represents n binary tree where SI is a symbol, P is the... So each symbol with its frequency has the weight of the tree. Weight of the tree. What is the weight of the tree? I'll ask ChatGPT. Just one node. Weight is stored inside the node itself, representing the frequency or probability of the symbol. I have no further questions. So we join two trees of ij. With minimum probability into a new tree T with height pi plus pj. And then append the original trees ij as the left and right subtrees of T. Okay, each symbol starts as its own tree. Okay, first iteration combines smallest trees. Combine two smallest trees into a new tree with height, the sum of heights of them. Left and right, okay. Traverse the final tree using DFS and assigning bit value 0 to the left and bit value 1 to the right subtree. Read a symbol encoding as the bits on each path from root to the... What? Oh, here's the example. Never mind. Okay. Weighted length, so 4 trees. We have just the probabilities of them. 3 trees. Now we have one tree representing these two nodes, and the tree representing this node, and the tree representing this node, so 3 in total. Sum of the probabilities. Now boom, 2 trees. Representing these 3 nodes, and they're representing this one solo node, and red digits assign bits of the code. Join 2 trees ij with minimum into a new tree. Okay, so this is a new tree, and this would be, so no, this would be 0.7, this would be 0.6. That's why it's together. Left and right subtrees of T. So this always creates a new tree originating from it. Okay, so this pops up to existence, then this pops up to existence, finally this pops up to existence, and we only have one tree. More examples of problems solved to optimality by a greedy algorithm. Though I'm kind of surprised to see Huffman coding as an combinatorial optimization problem. Really, I did not expect it to be here. Welcome surprise, honestly. More examples of problems solved to optimality by a greedy algorithm. Continuous knapsack problem. Whoa, that's I think the third or fourth variant of this problem. See page 28. Very well. Optimization version. The relaxed version of knapsack is called continuous knapsack problem. So this is an easier version. Choose the knapsack elements according to decreasing gain from a unit of space. Continuous knapsack problem. Also known as the fractional knapsack problem, an algorithmic problem in combinatorial optimization in which the goal is to fill a container, the knapsack, with fractional amounts of different materials chosen to maximize the value of selected materials. Okay, so we are able to allowed to chop items up. Basically shedding off their weight and bit of value as well. I mean, this could apply to things like liquid metal, I think, maybe, or something that can be easily divided. Maybe we could cut through a bar of gold or something like that. Yep, that could apply to the continuous knapsack problem, or this definition of dividing items. Change making problem. Returning the rest in cash in minimum number of coins and notes. Oh, so basically minimizing the amount of coins required to return the rest, the remainder, the requirement for the correctness of this algorithm. Homework or in trouble? What's this? Canonical coin systems for change making problems. I'm not reading this. Okay. whether it produces the expected and correct output for all possible valid inputs. Coin or node system must be canonical. This means greedy optimal system. The coin denominations must be structured such that the greedy approach, always picking the largest possible denomination that fits the remaining amount, results in the minimum number of coins or nodes for any amount. Monotonic property. For the system to be greedy optimal, it should satisfy the condition that for any amount A, the sum of the minimum number of coins A minus D, where D is denomination, and the coin D gives the minimum number of coins for A, shows the greedy solution matches the globally optimal one. No anomalous amounts. If the system has certain amounts where the greedy solution does not yield the minimum number of coins, like in the non-canonical system such as 1, 3, 4, the algorithm will not be correct unless a more sophisticated approach like dynamic programming is used. So basically we just go down the ladder, just trying to fit the biggest possible coin always, as long as possible. Monotonic property for the system to be greedy. Okay. I'll ask Primer to understand. Okay, so there's just one objectively one best way to return a particular amount. So for example, with the denominations 1, 3 and 4, to make 6, the greedy would choose for 1 and 1, but the optimal solution is to just take 2 times the 3. So 2 coins versus 3. And that forms a canonical system. 1, 5, 10, 25. Every... so they are just... multiples of 5, I guess. I guess I understand. Scheduling problem. I think that just signifies the constant time. I'll ask chat again. Single processor. Oh, there's just one. Okay, never mind. Available to process tasks. This means that all tasks must be scheduled on the single processor, one at a time, as no parallel processing is allowed. There are no modifications to the problem. Lmax maximum lateness. The objective in this scheduling problem is to minimize the maximum lateness. Lateness is defined as the difference between when the task is completed and its due date, which can be positive or negative if the task finishes early. So in the end, there's a balance of deadlines for these tasks. Okay, so this is on single processor, minimizing maximum lateness, non-decreasing due dates. So the most urgent tasks get done first. And this is Sigma CJ. Execute jobs according to the non-decreasing processing times. PJ, shortest processing time. SPT minimizes mean processing time. CJ, what was CJ again? Mean processing time. Here it's weighted shortest processing time. WSPT. Shortest SPT is the shortest processing time. Yeah, I guess in the end. These are just all on this single processor. Schedule jobs according to non-decreasing due dates. DJ, edit the order. E, edit the order. Let I be less than N be the first late job. Move the longest job in 1 to I to the end of the schedule. Shift the jobs earlier to close the empty interval. I want a breakdown of this. Break it down for me. With this pace, fingers crossed, we should be done by 3 a.m. Shortest paths. I am very familiar with, I think I am fairly familiar with shortest paths. This should not be that difficult for me. But, I don't know. Single processor, objective function, this represents the total number of late jobs. Ah, okay, so this has to minimize the number of those jobs, not the... So the first one was minimizing the processing time, total processing time, or mean processing time. No, the shortest processing time. So longest jobs would be done first. I don't know how would this even like change on a single processor. Mean completion time. The completion time of a job J, known as CJ, depends on when it starts and how long it takes to process. On a single processor, jobs are executed one after another, meaning the completion time of one job affects all the jobs scheduled after it. If you execute tasks with longer processing times first, shorter tasks will get delayed, increasing the overall completion time. However, if you order tasks more intelligently, you can minimize the total or average completion time. Oh, so shortest, longest, but why? Cashier prefers the shortest orders first, like someone ordering just a coffee, and the line moves faster and everyone waiting time decreases. Ah, okay, so the waiting time. Yeah, okay, so this is the time waiting for the job to be completed. Yeah, I think I have a grasp on it. So, waited, this is just with this addition of waits. And this is just the number of not decreasing, so shortest will get done first. And now this U something. If job J is late, completed after its due date, 0 if the job is on time. Just to minimize this, EDD order. Jobs are first sorted by their due dates in non-decreasing order. This step ensures that jobs with earlier due dates have a higher chance of being completed on time, which is logical because they have stricter deadlines. In fixing late jobs. Let I, where I is less than n, be the first late job in the schedule. A job is late if it finishes after its due date. Once you find I, you know that the schedule starts to fail from that point onward. Adjust the schedule. Find the longest jobs in terms of processing time amongst the first I jobs. Move this longest job to the end of the schedule. So basically it allows those late jobs to be, gives them a chance to be completed in time. Long jobs are more likely to cause lateness, so moving them to the end minimizes their impact on other jobs. Shift off the other jobs earlier to close the gap created by moving. Oh, okay. So it just moves it like in that fashion. I just wanted to really quickly rewind one thing. This is no, this thing, nope, not this thing, nope, not this one, not this one either. That was I'll need to come back to it later on my own. Okay, so with tasks, so the processing time for each job is 1. For n jobs, there are also n time slots of duration 1. Assign jobs to time slots in the order of non-increasing weights. Assign job J to the latest available time slot before its deadline. If no such slot is available, put job in the last free slot. Weighted. Oh, it's weighted. So basically, the impact of each job. So on a single processor again, Pj is equal to dj minus rj, and this has to minimize the sum 1 minus uj. Interval scheduling. Jobs must be executed non-preemptively from ready times to due dates. Maximize the number of executed jobs. Schedule whatever possible in the... Oh, so if the job is late, we just... So we have to maximize this. So it only counts when the job runs. So they must be executed between the ready times and due dates. Maximize the number of, and the duration is exactly that. Maximize the number of executed jobs. Schedule whatever possible in the order of non-decreasing deadlines, due dates. Assume that matroids. Assume that we are given finite set E called ground set, family J that is the proper, no, that is just the subset of 2 to the E. What? Matroid? It's a matroid. mathematical structure that generalizes the concept of linear independence from vector spaces to more general sets. Provides useful framework for solving optimization problems, particularly those that can be efficiently solved using greedy algorithms. Matroid is a par M, EJ, where E is a finite set called the ground set, J is a collection of subsets of E, known as the independent sets, which satisfy the following properties. They are not empty. The empty set is always independent. No, the non-emptiness. So empty set belongs to J. Heredity. If A is in J and B is the subset of A, then B is in J as well. Any subset of an independent set is also independent. Exchange property. So by recursion, this would mean that if E is in J, then by definition all its subsets will also be independent. Exchange property. If A and B are in J and the order of B is equal to the order of A plus 1, then there exists some element little e in the difference of those sets such that the union of A and little e is in J. This ensures a structure similar to the basis exchange property in linear algebra. Weighted matroids and the greedy algorithm. A weighted matroid is a matroid EJ, where each element little e of capital E has a weight function W, mapping E to the positive rationals. The weight of a set A, set A being a subset of E, is defined as W of A is equal to the sum of little e's in A. No, what? As some weight function little w such that maps E to the positive rationals. In other words, weights WE of elements E. So this function of A is just the weight of set A. Matroid EJ is with the above weight function is called weighted matroid. Greedy algorithm. Solve elements little e in E according to non-decreasing weights. So from smallest to greatest. Going on increasing for maximization. And for A is an empty set initially, so until the nth iteration we run this simple for loop. If the union of A and little e I is in J, then A becomes this basically the A absorbs this element into itself. Practically all sets A in J are feasible solutions of the considered problems. If matroid M is a weighted matroid, then set A built by greedy algorithm has the smallest weight, respectively largest for maximization. I need to ask primer. Weighted matroid. Imagine you own a workshop with a large collection of tools. However, there are constraints. Some tools are redundant, for example, 2 different screwdrivers of the same type. You want to pick a maximal useful subset of tools to carry. The subset must remain independent. Every tool adds unique utility. Matroid provides a mathematical way to describe the independence of such subsets. Matroid consists of a finite set, E, called the ground set, collection I of independent subsets. Okay, if a set of tools is valid, taking out some tools keeps it valid. Non-emptiness. The empty set is in I. Exchange property. If one valid toolset has more tools than another, we can always swap one tool to balance them. Imagine that each tool in your workshop has a value. Now your goal is to not just to pick a valid toolset, but to pick the most valuable valid toolset. Dependence on maximum total weight. Greedy algorithm for weighted matroids. The greedy algorithm works optimally for this problem. matroids, I think, are also covered by this, so we need to understand them really carefully. Surprisingly, they are not, but I wouldn't take it for granted. I need to get a better understanding of them. I think I'll watch some YouTube videos about them, and the concepts I don't understand fully, I'll just watch some YouTube videos. Yeah, I've seen what you sent me. Basically, ultimate lock-in. I've seen this variant of Matroids, you say? Ah, okay. Yeah, I think I'll just streamline. Yeah, okay, very well. I mean, it's not hard really. It's not, this definition is not convoluted. It's just, yeah, I'll just write it down. Maybe I should just write it down right now. I think I'll mark all the stuff I need to rewind in the notepad. Okay, so let's write down the definition of a matroid. Okay, so matroid it is EJ and E is a set of elements. I don't know elements. J is a set of subsets of E such that if A is in J, and B is a subset of A, then B is also in J. If A and B are in J, and B equals A plus 1, then there exists E in the difference of those sets such that A union little e is in J. I've missed the middle one. Oh, and the first condition is that an empty set is also in J. Oh, and E is finite. Okay. I'll call this in dotted lines as meta definition. Meta, the precise definition that is. Yeah, it's not bad, really, it's just a matter of understanding them. So weighted matroid would, so again, weighted matroid, weighted matroid, weighted matroid. A weighted matroid, weight function, W, maps E to the positive rationals, weight of A is equal to the sum each element E in A, and it's on this so this function operates, and this is weight of set A. Weight, yeah. Sort algorithm. So all elements in E are sorted by their weights, and we just keep this is as simple as just adding elements with the lowest and greatest, provided that this the union of A and this element is in J as well. Okay. And this also gets the mark of meta official definition. I announce a 5-minute break, and then we will be back online.